In today's video, we'll discuss about refraction at spherical surfaces. We'll derive the formula for thin lens and also lens maker formula. So we'll begin the discussion with refraction at a spherical surface. We'll derive it completely, पूरा उसको complete derive करेंगे step by step. Let us see. So first हम लोग रिफ्रैक्शन एट ए स्फेरिकल सरफेस उसको डिराइव करते हैं. रिफ्रैक्शन एट ए स्फेरिकल सरफेस मीन्स इट कैन बी कॉन्केव, इट कैन बी convex shape. So this is a convex shape, and let's say this is a convex medium, let's say glass or something like that, of having convex shape, and this is, let's say, n1, or you can say write mu1 also, refractive index. This side is air, and this is mu2, any other material like glass or water. Okay, and the surface is convex shape. We'll derive this case, ये case derive करेंगे, and the result will be applicable for other cases also, like concave case also it will be applicable. Instead of convex shape, if we'll keep a concave shape also, the same result will get. So let us derive first what the result we are getting. Let us see for refraction at a convex shape. So through its midpoint we'll pass a axis, principal axis. Let's say the object is somewhere here, and it will take two rays, one ray, let us this is one ray. So after refraction as medium 2, we have already mentioned that mu2 is greater than mu1. So what will happen? We know the laws of refraction, that if light rays is traveling from a rarer medium or less dense medium to denser medium, let's say air to water, then it will bend towards the normal. So I will be greater than R. This is what we know. And one more law also we know, that from Snell's law, sin I upon sin R is a constant, which is mu2 by mu1, generally we write refractive index of 2 by refractive index by 1 we write. Okay, let's say this is refractive index 2, this is the refractive index of 1. So this principle, this result we will use here also. Okay, so let us erase, or let us keep it. It is okay. So now here you can say this is your normal to the surface, and this will be angle of incident. Now instead of moving in this line, it will slightly bend, and somewhere here image will be formed, and one ray I will pass through the principal axis, which will pass undeviated, and it is intersecting at a point here. So here the image will be formed, I, right, I image formed. Now what is R here? This will be your R refraction. This is a 90-degree normal, this line. Now let us write down, this is alpha, let's say this is beta and gamma, let's say this is beta and this is your gamma angle, gamma, not r. So from your basic trigonometry and the triangle concept, you can write that. You can see, let me take another color, this red, this line and this one, this is a triangle and this is your external angle. So I can write from this triangle, this is let's say M and B. So from triangle OMB, from triangle OMB, you can see angle I equal to alpha plus beta. Clear? Similarly, if we take this triangle, okay, so you can write from triangle B and this is, let's say C, BCI, from triangle BCI you can write R plus, or in this way you can write gamma equal to, sorry, beta is the external angle here in this triangle, so beta equal to R plus gamma. So these two condition now you know, and one more condition will use, that is your, that for small angles, these angles are, let's say alpha, beta and gamma are small. For small angles you can write sin alpha is approximately equal to alpha, tan alpha is approximately is also equal to alpha, or tan theta is approximately equal to alpha. This is small angle approximation. So for small angle this approximation we can use, okay. And so here you can see, if you will use the Snell's law, this one, okay, so this is your mu1, so you can write mu2 upon mu1 equal to sin I by sin R. Let's take another color, or you can write this one, that sin I is simply I and sin R is approximately equal to R, so simply I by R. So you can cross multiply and you can write I mu2 equal to I mu1. This is cross multiplication, I mu1 equal to R mu2. Now from here this expression, okay, you can use it, that you can use okay, so you can now put the value I and R from these two equation. So if you put, you will get like this: I is alpha plus beta mu 1 equal to R is bring gamma to the left side, so gamma mu 2, right? So this is what you got, or you can simplify a little bit. You can bring alpha and gamma to close, so alpha mu 1 plus gamma mu 2 is equal to, in the right side you can take the beta, so this will be mu 2 minus mu 1 common beta, right? So here we can put alpha, beta and gamma from this one. You can see here alpha, beta and gamma. You can write, you can look at the diagram, okay, or I can draw it again. Here you can see, so tan alpha you can write, as I have told, sin alpha and tan alpha. For small angle it is like equivalent to alpha approximately. So I can write tan alpha equal to P by B, that is Bm by Mo. You can write Bm by Mo here, okay. Tan alpha is equal to Bm by Mo. So approximately you can write alpha is equal to Bm by Mo. Similarly, you can write beta will be equal to your Bm by Cm, and gamma will be equal to your Bm by Mi. Now we will put this alpha, beta, gamma value in our expression, okay, that you can see here. We will use this alpha, beta, gamma here, okay. So you can see here in this expression we will use alpha, beta, gamma. So if we will use, then you can see alpha is your mu 1 into Bm by Mo plus mu 2 is gamma is Bm by Mi, and equal to mu 2 minus mu 1, beta is Bm by Cm, right? So Bm is in the numerator and in both sides it's there, so Bm is सब cancel हो जाएगा, it will cancel out. तो बचेगा क्या? What will remain? mu 1 by Mo plus mu 1 by Mi equal to mu 2 minus mu 1 divided by Cm. अभी देखो ये Cm क्या है? What is Cm? Cm ये normal है, so Cm will be the radius of curvature, right? Normal to the tangent, okay, at that point it will pass through the center of that sphere or circle, so C will be the center here and this will be a radius of curvature. So radius of curvature, as this is convex shape, we will use the sign convention, and the sign convention will be R will be positive in the right side, Mi is also positive, its right side, Om will be, or Mo will be negative, it's in the left side. And you can use the sign convention and you can see, let me go up, where will write, here we can write, we can erase, or directly we can write. Okay, so here you can see Mo is negative, so here Mo is object distance, that is minus u, which is in the left side, minus u. Mi is the image distance, which is in the right side, V, and Cm is radius of curvature and it's in the right side, so it's plus. So these two are plus and first one is minus. So this is using sign convention, you can get that mu1 by Mo is minus u, mu1 by minus u plus mu1 by Mi is plus V. Oh, this is mu2, sorry, mu2 by V equal to mu2 minus mu1, Cm is R. So this is what, this is the result for your for a spherical space, for a spherical shape, if light is traveling from a medium of refractive index mu1 to mu2. Okay, this is the case, and it's a convex shape we have calculated. But remember, this formula you can derive also for other cases and you will get the same result. Even if you take concave shape, or if you take denser to rarer, if the light is traveling from denser to rarer also, the same result you are going to get, that mu2 by V minus mu1 by u equal to mu2 minus mu1 by R. So this is the result you are going to get for any spherical shape. So this result is for any spherical shape. Okay, concave, convex, both, concave and convex both, this result is true or valid. Now very important formula will derive, that is lens maker formula. Many times in the exams also it's asked, this question is asked, and from there we will discuss the thin lens formula. So this result we will use in the lens maker formula. This result we will use, very important result. So now see how will you use this result. Let's say we are supposed to calculate the or derive the formula for thin lens, and this lens is thin, means this width will be very small. Okay, we will take that approximation. Let's say this is your object, so light incident on the lens will face two surfaces. One surface is, let's say this is this surface is your, this is B, this is D. Okay, this is, let's say, AB, M, and this surface is Adm. So, and this image will be formed, let's say this is your axis which is passing through, and let's say this is the image will be formed here. Now the principle is we got this relationship for one surface, like this surface, a convex surface. Now it will again means the image that will be formed in the left surface, that is Adm surface, will be used as the object for the second surface. Okay, second surface is like a concave surface which is and where the light is traveling from denser to rarer medium. Okay, so if we will split this diagram in two parts, then it will look like this is your surface, first surface ABM, and light, this is your axis, let's say this is your object. So in this surface what will happen, the image will be formed somewhere here, and this is your normal, and this is your mu2, this is your mu1. Okay, so here as inside is denser, let's say this is air, and this is your glass, this lens is made up of glass. So mu2 is greater than mu1. Okay, hence what will happen, this is your normal. Okay, so bending will be towards the normal. Instead of going this way, it is bending towards the normal. And what is your R? This will be your I1, let's say this is your R1. Okay, so this is for left surface. Now for the left surface, let's say the image is formed is I1. Okay, the image formed is a I1. This is your center one also C1, ऐसे लिखते हैं ये O. Now the image for this one, very important this statement, the image of formed by the left surface will be solved as the object for the second surface, a virtual image. Okay, so will be solved as the object for the second surface. So the diagram for the second one will be like this. This is your second surface, and this one image will be the object, so it is your I1. Okay, now here outside is again air, so refractive index is mu1, so that means denser to rarer medium. Here what is happening, now there is the light is traveling from denser to rarer, so there will be deviation from, this is let's say normal, so the deviation will be away from the normal. Okay, let's say this was initial R1, so the deviation will be there, and final image will be formed, let's say somewhere here. So this will be your final R, refractive index, angle of refraction, and this will be your I, let's say. Okay, so there will be more bending, or you can say here the ray will be away from the ray will be away from the normal, because it is the light is traveling from denser to rarer medium, right? Now this is D, and here your final image is formed, and here your center will be like this is C2, we can write, and here in the left side your center for will be in the left side, so the focus will be also in the left side. Okay, these things will consider when we will use the sign convention. Okay, so now we will use our formula. The formula just we derived for a spherical surface we will use here, as I have told you that the result is applicable not only for convex shape but also other shapes. Like for this case also the same formula will be used. So here in the left side it's mu 2 and in the right side again air is there, so mu 1. But for the first surface left side is mu 1, right side is mu 2. So here you have to concentrate a little bit, which is mu 1, which is mu 2, then you can easily use the formula so that the derivation will be easy. Now what was our formula? As you can see, the formula is here. The formula is here. You can see, or let me write again this formula. So the formula we have derived is mu 2 by V minus mu 1 by U equal to mu 2 minus mu 1 by R. This is the formula we have derived for a spherical surface. For a spherical surface, this is the result. Okay. So now let us use this result in for the first surface. Okay, for the first surface let us use it. So for the first surface, that is ABM surface, here light is traveling from mu 1 to mu 2 of refractive index. So you can write your mu 2 by V means here your BI, okay, BI1 minus U1 mu 1 divided by U, okay, U is BO equal to mu 2 minus mu 1 by R, okay, mu 1 minus mu 2 by R. Or you can say this is what we have taken BC1 R, or you can write here we are writing BC1, okay. Now for the second case you can see here as we are writing BO, so we have represent BO is minus U, right? So it will be plus the first expression. You can see this one. This is what minus we got after using the sign convention, but this is our without the sign convention. You can see this is your expression, this one, mu 1 by MO object distance by mu 2 by MI, that is your image, by mu 1 minus mu 2 minus mu 1 अपन CM, ठीक है. तो वो वाला हम लोग लिखे हैं. Then you can see here okay. So this is for the surface. This is for the surface, your ABM, or ABM surface. Now the next surface, that is ADM surface. Okay, ADM surface, here light is going from mu2 to mu1 and the object distance is in the opposite direction. Okay, so object distance we will write, that is uh, so you will write your mu2 by object distance. Left side is mu2 by object distance is this one, di1. So di1 exactly will write a negative sign for that. Why? Because it is in the generally object in the left side according to along the incident ray. So here di1 is a virtual image. Okay, the image of the first one is used for the second one, so we'll use it in opposite direction. We'll use it a minus di1. Okay. Now plus right side, it's mu1 divided by image will be formed at di equal to mu2 minus mu1 divided by its radius of curvature in the left side. So radius of curvature is, or we can write simply dc2. Now this is your equation number 1 and this is for which surface? ADM surface. Right, now this is, let's say, equation 1, this is your equation number 2. Now add this equation 1 and 2. Okay, you add equation 1 and 2. देखो ऐड करने से क्या होगा, ए वाला टर्म और ये वाला टर्म कट जाएगा, because for thin lens we'll use this approximation. We'll use the approximation of for thin lens. ये B and D, the difference between B and D will consider, it's very thin, it's a thin lens, so we'll consider they are in the same point. B and D both are same point, so that you can write B to I is same as D to I. Okay, so here you can write BI1 and DI1 is equal, BI1 equal to DI1. B and D are approximately same point. This is for thin lens. For thin lens you can approximate this approximation. That's why when we will add these two terms, BI1 is DI1, so they will cancel each other. So you can write mu2 by BI1 plus mu1 by bo minus mu2 by di1 plus mu1 by di equal to mu2 minus mu1 common 1 upon bc1 plus 1 upon dc2. Okay, now this one cancel. Okay, I1, this one and this one cancel because bi1 is approximately equal to di1. So what we got, we are getting mu1 by bo plus mu2 mu1 by di equal to mu2 minus mu1 1 upon bc1 plus 1 upon dc2. Okay, now the important thing is that here we have used a negative sign. You have to remember that because we have used this di1 as the object for the second one. Okay, and that's why it's in the different direction than the incident ray. Okay, incident ray is from generally left side, but virtually it is coming from the right side. Okay, that's why we have used a negative sign for di1. This is the one you have to remember this step of derivation. So now easily you can use the sign convention again. So mu1 bo, what is bo? I can show you what is bo, what is di we have taken. So this is your o, if you remember. So bo is generally u, di is image, and that bc1 is r1 and dc2 is r2. Now see, r1 is the right side, so r1 will take positive, r2 is in the left side, so r2 will take as a negative thing. So this is important sign convention. So I am writing directly here that bo is minus u plus mu1 by di is v, this is plus v, equal to mu2 minus mu1. As I told you, bc1 is the right side, so it is 1 upon r1, and dc2 is in the left side, so this is minus 1 upon r2. Okay, and this is what your lens, this is called lens maker formula, or you can write this in this way. This will simplify a little bit, that is mu1. Okay, so this is one equation. Now we'll use one more approximation, that if light is from infinity, this object is at infinity, then the image will be formed. This is C, this will be your focal length. Okay, that means for u tends to infinity, your V will be approximately at focal length. So this approximation we will use here. Then what we will get? So using this approximation, our equation will convert to, this one will be 0, 1 by infinity is 0, and this will be mu1 by V is f equal to mu2 minus mu1 1 upon r1 1 upon r2. Okay, or you can write or you can write 1 upon f is equal to mu1, you can divide here, bring to the right side, mu2 upon mu1 by minus 1 into 1 upon r1 minus 1 upon r2. So this is what, this is the lens maker formula. With proper r1 and r2, the manufacturer, they can make the different different lens of different power, because 1 by f is power, so lens of different power can be made with proper combination of or different combination of r1 and r2. Okay, and mu2 and mu1 are the refractive indices of the material. Okay, and if again if the mu1 is air, okay, if mu1 is air, then also this formula will be further reduced to mu2 minus 1 only. Okay, if you will consider mu1 is air. Okay, this is the general formula. You can consider this mu1 is 1 for air, so this expression will further reduce to mu2 minus 1. Okay, now you can see in equation 1 and equation, let's say this is equation 2, in equation 1 and equation 2 the right side is equal. Okay, so the left side should be equal, so you can write from equation 1 and equation 2. Okay, before that let me write, this is called, this is your lens maker formula. So this was our also objective, to derive this formula, and from equation 1 and 2 you can write, from equation 1 and equation 2 you can write, the right side is equal, so left side will be definitely equal. That means you can write mu1 minus u is plus mu1, this is mu, by v equal to 1 by f. Okay, or if you further simplify, sorry, not mu, this is mu1 by f, equation 2. Now in the numerator mu1 will cancel out, so you can write, this is 1 by v, then minus 1 I will write later, 1 by u equal to 1. This is the formula you know for your lens. Okay, for thin lens formula you know in your class 10 also. This is a familiar formula, so this is called your thin lens formula, thin lens formula. Okay, so in this video we have completely derived the thin lens formula, the lens maker formula. Okay, and we have derived in the beginning the expression for or the equation for a convex surface or spherical surface. Okay, and also here you should remember that this expression 1 upon v minus 1 upon u is equal to 1 upon f, this is true for all the lenses like concave, convex and concave lens. Here we have derived the expression for convex lens, but this expression is true for also concave lens. Okay, So let us stop here. uh, Problems we'll discuss in live classes. I'll take one live classes maybe tomorrow or day after tomorrow. I'll give you the notification for that, and we'll discuss some problems based on this thin lens and lens maker formula. So this is very important for the derivation, is very important for the exam also, and problems are also means come in your entrance examination as well as many times in the board exam. So if you are preparing for board to 2021, then you should practice this part very carefully, because I think mirror formula equation is removed or reduced this year, so that definitely lens from lens the problem will come. Okay, let's stop here. Thank you.